Welcome to this introduction to the world of physics. The field of physics, one of the greatest intellectual achievements of humankind, is the study of the fundamental laws of nature. And with the knowledge of physics, we hope to understand the vast world around us. Our aim in this small video is to provide some ideas about the basic questions regarding physics, like how we model the world around us and how we arrive at the fundamental laws and so on. Before we dive into any of these, we must say a few words about certain things we take for granted, or about things that are too obvious to us that they don't need a proof or anything. We are going to assume certain things and provide some arguments regarding why they are true. The first is about the real physical world around us. We must assume that such a world exists. We all know we are assuming it every moment. We all know this fact. We seldom ask for a proof. This world exists independent of what we feel inside our heads, independent of our conscious experience. Let us imagine a situation where all conscious things on Earth and anywhere in the universe become extinct due to some mysterious reason. Maybe some large supernovae wiped them all out with an intense gamma-ray burst, or a few asteroids struck their planet, sending everything to oblivion. The obvious truth is that the world or universe will still exist, even if all the animals with their conscious brains are gone. There is a physical world out there that always existed independent of all those organisms that once lived, and which will continue to exist. But we are still talking about this physical world as something already given, like some assumption. But if we give it a thought, we can see why this is true. We can see why this physical world is very real, independent of our senses. Just consider the way everyone sees the world around us. Of course, everyone does not see the world exactly the same. The images we see with our eyes are not the same pixel for different individuals. But we all can agree that we are seeing more or less the same things if we are standing close. Even when we are farther apart, there is a level of agreement in what we see. The difference in their perception is consistent with the difference in their positions too. If two people are standing near, the images they perceive inside their brains are only slightly different, and one can verify how the other one is seeing by taking his place. He would agree with the first person almost exactly. If one person was a great artist and painted what he saw in front of him, another one can take his place and verify that the painting exactly matches what is in front of him and is very similar to what he was seeing moments ago before shifting his vantage point. To put it in even simpler words, if the outside world were not real, these two individuals won't even agree upon the existence of a drawing board in the first place. If you see a mountain over the horizon that has a specific shape, someone else too shall observe the same mountain with the same specific shape. We made the entire argument in relation to the sensation of vision. But we can arrive at the same conclusion regarding all other sensations. Of course, we cannot express a certain smell like how we can express a certain scene with a painting. But we can always use languages and other cues to express what we are experiencing. Like, for instance, we can say a taste is bitter or a smell is sweet, and the others can relate to it. And language, or more precisely communication of information, has a very important role in understanding the nature of reality. So, we can safely say that the physical world out there is real, and it is not an illusion. Because otherwise, everyone would never have consistent sensory experiences. So we have come to the conclusion that the physical world is a real and tangible thing. There is something out there that exists independent of us. What this something is has been a topic of hot debate throughout the centuries. This is also a very deep philosophical question. But we are not doing philosophy here. We are pursuing physics, the study of nature and its laws. So we will try to formulate the nature of this physical world in a way we can comprehend. That is what we are going to do now. So let us again get back to physics, the study of the physical world. We remember that physics is about the study of the most fundamental laws of the nature, or the universe. We are stating in plain terms in the beginning itself that physics, or the classical mechanics version of physics we are going to study now, is the study of the interaction of matter or material objects in space and time. Space, time, and matter constitute the world we live in. Everything happens in the space around us. And everything proceeds in time as well. There are also certain rules or characteristics of the world in which we live in. These characteristics are very fundamental and of a universal nature. They are simple in form and they are applicable everywhere. And they have no exceptions too. If it is true in one part of the world, it is true even millions of miles away too. The rules also have a peculiarity that they are essentially mathematical in nature. As Galileo said, mathematics is the language in which the laws of the universe are written. With these laws or rules, we can explain everything that happens in the universe. From a very limited set of fundamental truths, we can explain a whole lot of phenomenon. These rules also help us to predict new things. Things that we haven't been able to observe in the first place. We can predict how some part of the universe will behave without waiting for it to happen. We can see where the planets would be in a future time. We can tell if an asteroid will hit the Earth or not. We can predict how a machine will operate even before building an actual one, and so on. These help us save time, effort, and even enable us to survive as a species. All this is possible because of the power of mathematics and the extremely simple form of the basic laws we are going to encounter in subsequent discussions. The power of mathematics combined with the arsenal of the laws of the universe help us build unimaginable things, from moon rockets to nuclear weapons. It seemed so powerful that scientists began to believe that the world around is entirely predictable. There is this notion called Newtonian determinism. It essentially says the universe is like a giant machine. And just like how we can predict the motion of real machines that we build from time to time, we can also predict the motion of this giant machine called the universe. The only things we need to know to predict the motion of this machine is where the individual parts of these machine are and how they are moving at the present moment. We then combine this knowledge with the laws these individual parts are subjected to. We can then, in principle, predict how the universe will evolve in the future and how it has evolved in the past, all with perfect accuracy. Newtonian determinism enables us to predict the past and uncover the future with perfect accuracy, at least in principle. It allows us to see how the world will look like at a particular point in the future, and also how it looked like at a particular point in the past. Pierre-Simon Laplace, the great Newtonian physicist, famously stated, "We may regard the present state of the universe as the effect of its past and the cause of its future." An intellect which at a certain moment would know all forces that set nature in motion, and all positions of all items of which nature is composed. If this intellect were also vast enough to submit these data to analysis, it would embrace in a single formula the movements of the greatest bodies of the universe and those of the tiniest atom. For such an intellect, nothing would be uncertain, and the future, just like the past, could be present before its eyes. This is one of the boldest statements in the history of science. This even nullifies free will, our innate ability to make conscious choices and affect our lives. The blessing bestowed upon us that makes us the creators of our own destiny, and the curse that makes us responsible for our own doom. But in the modern times we live in, we are entirely convinced that perfect determinism does not exist. This is due to the emergence of quantum mechanics, which says the world is fundamentally governed by probabilities or chance. But in all subsequent discussions which are related to this introduction, we will be pursuing and exploring only one particular aspect of physics called classical physics. This is the branch of physics where Newton's laws of motion and Newton's worldview are valid. This is because we want to do things in a perfectly Newtonian spirit, at least for the time being. We have already remarked that the universe is fundamentally non-deterministic, but this non-determinism is evident only at extremely small scales, at the scales of atoms, the major fundamental building block of the universe around us. If we are careful to not hover anywhere near these scales, the universe is essentially deterministic to any level of accuracy we desire within these limits. That means we can predict events and explain phenomenon in this domain with the laws of classical physics, with the help of the right mathematics. But the most important question is this: how do we find these laws? And the answer is extremely simple. We find out these laws by observing nature. This is a very simple proposition. But once we start observing nature, we will start to realize the actual process of carrying this out is not that simple. So, we are observing nature to find out some extremely simple laws. It means that the events we are observing must be simple enough. We cannot easily obtain simple underlying rules from observations of very complicated events. You cannot deduce the fundamental laws of nature by observing a volcanic eruption or dissecting an insect. We must look at very simple events instead. This is how Galileo actually deduced the laws of free fall. To investigate the motion of falling bodies, he did not just simply observe random things falling to the ground. Rather, he made specialized and simplified apparatuses involving smooth inclined planes, precise water clocks, and so on. Galileo was bringing nature to his own terms. He was essentially isolating the motion of objects to an extremely simple setting. And in that way, he eliminated unwanted complexities and the influence of unwanted influence from his observations. Obviously, you would not want to have a strong gust of wind or a scorching flame on a falling object that you are observing. Even Newton was referring to the mathematically elegant motions of the planets to formulate his laws of mechanics and gravitation. For Newton, the cosmos itself was his laboratory. There is one instance in history where this simplified observation was naturally possible, in the field of astronomy. Observing the sky, especially the night sky, was a relatively simple and straightforward task, because the night sky is an extremely simple place to look at. We could keep track of the objects in the sky one by one. Seldom did they obstruct one another, and even when they did, it was brief and predictable. Their motions were also systematic, and not a chaotic mess like the ones we see down here on Earth. Even the motions of wanderers, the planets, were simple enough for us to observe them consistently for long periods of time. We could represent the positions of the fixed stars and the wanderers with numbers. We could even give a geometric meaning to their motions by placing them on celestial spheres. So, the motions of the objects in the night sky were simple, and we could express them with numbers and geometry. And when we have simple observations and mathematics to represent them, we can easily deduce the fundamental laws underlying these simple motions. It is not an easy task, but it was sufficiently easy for the human mathematical intellect thousands of years ago. This is the reason why astronomy emerged as a science thousands of years, before even Newton and Galileo. The rules these ancient astronomers deduced were not fundamentally correct, but they were simple enough that they could predict important astronomical events like eclipses, transits, planetary positions, etc., over considerably long periods of time. And now comes the realm of Earth. It is a much complicated affair than the night sky our ancient ancestors so diligently observed and analyzed. It is certainly obvious it would be very hard to observe simple events back here on Earth, because we know the world we live in is extremely complicated. We sense this extremely complicated world with an extremely advanced array of sensory apparatuses. The result is our conscious experience of extreme complexity. If we contrast it with the observational world of ancient astronomers, the difference is enormous. The night sky was essentially some scattered bright lights against a pitch-black background. The terrestrial world we live in is not even remotely close. So, how do we look for simple observations and events back here on Earth? At first, this seems to be an impossibility, but a beautiful and creative solution exists. We deliberately try to make the events we are observing simple. We create extremely simple environments and apparatuses so that the events happening in front of us are extremely simple. This is another way of saying that we set up careful experiments. Experiments are the cornerstone of physics. Without experiments, we would literally be searching in the dark in pursuit of the fundamental laws we are after. So these careful setups, these experiments are constructed in an extremely simple way that lets us isolate parts and events of our universe in a very convenient way. And with this convenience at our hands, we can make very simple observations. We are observing how objects behave in our experiments, but for that we must first decide on what we are looking for when we are observing the behavior of objects. So it becomes necessary to attribute some characteristics to the objects and the world around us. And to make the observations easy, we must make sure these characteristics or properties are simple enough, and also that they could be handled with the tools of mathematics. Because, as we have seen, the laws of nature are written in the language of mathematics, and if something cannot be handled with mathematics, It is of no use as a property of objects using which we can deduce these laws. Colors of objects are not a good choice, because there is not much we can infer from the interrelationships of colors of an assortment of objects. Transformations of colors of objects, when we are observing complex phenomenon, occur in extremely complex ways, and in very simple setups, they do not transform at all. There are very interesting experiments where the color of something undergoing a transformation is extremely useful. One example is identifying elements from their salts. But colors are physically a combination of electromagnetic wavelengths, and their behavior is sufficiently complex to serve as a simple fundamental property of objects. We cannot choose smell, taste, etc. for our purpose for the same reason. But the position of an object, its size, shape, etc. are suitable candidates, because they are simple enough and they can be easily represented with numbers and handled with the tools of mathematics. We cannot do the same with color, smell, etc. of material bodies. It is not obvious how we can represent a real sensory experience with a number, because these sensory experiences have no parallel with numbers. This supplies us with the intuition that position, shape, etc. seem to be more fundamental and mathematically tractable properties. Even Galileo mentioned this when he talked about primary and secondary qualities of objects. He listed position, shape, size, etc. under primary qualities, and smell, taste, color, etc. under secondary qualities. If you think about this is the reason why we leave out consciousness from physics. We seldom talk about its role except in deep philosophical topics relating to quantum mechanics. We haven't been able to tackle the problem of consciousness until now, even after we have made great strides in understanding the fundamental nature of reality of the physical world we live in. Consciousness is something we are most familiar with. But it is also the most elusive phenomenon in that it has escaped all our attempts in trying to understand it. We still do not know how consciousness arises in our brains, what fundamental processes are associated, etc. Because if we did, we would be able to create consciousness from scratch, which we certainly can't. This is mostly because conscious experiences are fundamentally incompatible with the tools of mathematics we are so familiar with. As we mentioned before, it is impossible to represent a conscious experience as a mathematical construct, and that is the source of our struggle with consciousness. It does not lend itself to the beautiful language in which we write out the laws of the universe and with which we make elegant predictions. We can leave out consciousness for the reasons we stated before and again turn back to physics and mathematics. Mathematics is one of the most sophisticated and most useful intellectual tools humanity has ever devised. Even at the time of Kepler and Galileo, when our understanding of the fundamental laws of nature were not sufficient, our knowledge and expertise in mathematics was sufficiently advanced. So we have a good understanding of why mathematics is of primal importance and why choosing simple physical qualities for describing objects and their interactions is absolutely necessary. It is for these reasons that we choose position, shape, size, etc. as the properties or qualities of objects. If we look carefully, these properties are related to the three-dimensional space we live in. We have a sufficiently advanced awareness of this three-dimensional space, mainly because of our advanced cognitive and visual capabilities. The three-dimensional world is so real because our cognitive apparatus designed to perceive this three-dimensional world is very sophisticated. Not only can we understand the shapes and sizes of objects in relation to each other, but also their relative placement in the physical world. This is possible we see with two eyes, and since each eye sees a slightly difference of the scene in front of us, the brain can compare these two images and perceive the sensation of depth. Three-dimensional space is one of the most real things out there because everyone seems to have a very consistent and advanced perception of this aspect of nature. And as we have argued before, consistent sensory experience points to the existence of something real. So, three-dimensional space is one of the foundational building blocks of the universe we live in. This is because points in space can be represented with numbers, and it can be handled with mathematical tools. Another, deeper reason is that without space, nothing can exist. Then comes time. Time is what we feel every instant, although this might feel like a circular definition. But we certainly know what time is, although this knowledge could only be experiential and not a precise logical statement. Time is that flux that carries everything forwards, just as space is that substrate which supports everything. Neither of these are precise and logical definitions. They are at best poetic definitions, because if we look close enough, they open more gaps than they are able to fill. But time is so familiar to us that we always imagine the world to be carried forward in time. Every event occurs in specific points in time. We perceive reality as a succession of frames that move forward in time. Our cognitive perception of time is also consistent across individuals. If one agrees to a certain order of events he observes, the others too shall agree to it. There will be exceptions, although these exceptions are deeply tied to Einstein's relativity, and we will come back to it later. So, time is a real property of the physical world in which we live in. It is also of primal importance to physics because it is the flux that carries the world forward and also that it easily represented with numbers. And without time, nothing would happen, as everything will remain frozen. Now we have space and time, the stage on which everything happens. But we need the actors too. This is matter. Matter is the tangible substance we see all around. It is just as real as space and time. And without matter, there would be emptiness everywhere. We may loosely define matter to be anything that has mass and occupies volume. But then we are left to define what mass is, which is an advanced topic in itself. So, at present, we may define matter to be the tangible property of the universe that makes the existence of material objects possible and perceivable. And matter can also be represented with numbers, as the mass or weight of bodies, just as we did with space and time. Everything we have said before about matter are not precise definitions and may include a level of circularity. But these are good enough, for they loosen the conceptual knots and help us actually do physics, which is explaining and predicting events. So we finally have the three pillars of the natural world or the universe: space, time, and matter. Before we conclude, we want to mention another important feature of these quantities. It is called continuity. Continuity means existing smoothly. It means the quantity we are describing can go take any possible value, which is the same as saying the thing we are discussing does not come in discrete chunks. Space does not exist as discrete junctions in space. When something moves, and when we represent its position as a number, the value of its position goes through every possible value between its initial and final positions, and not just a set of equally spaced points. It does not move in discrete jumps. Matter can occupy all points in space, and not just certain fixed points. It also means space, or any quantity that is continuous, is infinitely divisible. You can keep dividing a chunk of space into smaller substances, and the process will not stop. The same is true for time. Time also exists continuously. We don't see discrete frames of the world around us. We don't see an object stop at one point in space and magically reappear at another point after a specific step in time. The transition of objects through time is continuous, and objects and the universe pass through all possible moments in time. This continuity of space and time is applicable even in the most modern physical theories, as far as we know. But when we talk about the continuity of matter, we need to be a bit more careful. We know space is continuous and matter exists in space. Then we might reason that matter is also continuous. But this is not true exactly. The space matter exists in is continuous, but matter itself is not precisely continuous. We know that matter is made up of atoms at a fundamental level, and these atoms themselves are made up of more and more fundamental particles like electrons, protons, quarks, and so on. If we go on subdividing matter, a point reaches where we can no longer divide the constituents. We cannot divide an electron into something more fundamental. As far as we know, the electron has no internal structure, and you cannot divide it into half an electron and then into 1/4 of an electron and so on. An electron is fundamental. You cannot divide it. The same goes with protons and neutrons, with some caveats. Protons and neutrons are made up of other more fundamental particles called quarks, but quarks themselves cannot exist freely. In any case, matter always comes in discrete chunks. Matter is not continuous in the absolute sense of the word. But here in our study of classical mechanics, we are assuming matter to be continuous. This is because in the physical problems we consider, we are dealing with sufficiently large objects made up of a myriad of atoms or molecules that we can treat it as essentially continuous. Atoms are so small that enormous numbers are present even in a speck of dust. So, regarding classical physics, matter can be treated to be continuous. But there is another remark we wish to make regarding space, time, and matter. Until now, we have assumed space and time exist independently, that there is absolute space and absolute time. Two individual constructs that together make up the stage of the universe. But according to our current modern understanding, space and time are not independent, but exist as space-time, which is the fundamental fabric of the cosmos. Space and time are entangled quantities in Einstein's theory of relativity, and the notion that they exist independently is not accurate. It is accurate for speeds which are negligible compared to the speed of light, the ultimate speed limit in the known universe. But for our purposes here, and for the investigation of even the enormous heavenly bodies, the point of view that they are independent is fairly accurate. Even the Newtonian theory of gravity was usurped by Einstein's theory of general relativity, which essentially says gravitation is not a force, but the curvature of spacetime itself. It is matter which curves this spacetime. Spacetime tells matter how to move, and matter tells spacetime how to curve. This is the gist of general relativity. But for most of the celestial mechanical problems we will be looking at, Newtonian gravity is an extremely accurate way of looking at things. Thus, we have reached the grand conclusion that space, time, and matter is everything that is needed to look into the secrets of nature, at least from our classical mechanics point of view, because these constructs enable us to apply our mastery in mathematics to the problems of nature. We can even give a name for this threefold reality, the kinematic substrate of the universe. And physics, or Newtonian physics to be precise, is the study of interaction of material bodies, matter, in space and time, or essentially the evolution of this kinematic substrate. A very important point on the aesthetic appeal of these physical laws and their applicability is worth mentioning here before we proceed to the real investigation. The practical appeal of physics or science in general is obvious. Just as Feynman humorously remarked, you do not need to write an essay on the practical use of science. It is obvious, but the aesthetic aspect of our endeavor is not very obvious. We will elaborate no further but present this beautiful quote by Henri Poincaré. The scientist does not study nature because it is useful to do so. He studies it because he takes pleasure in it, and he takes pleasure in it because it is beautiful. If nature were not beautiful, it would not be worth knowing, and life would not be worth living. I am not speaking, of course, of the beauty which strikes the senses, of the beauty of qualities and appearances. I am far from despising this, but it has nothing to do with science. What I mean is that more intimate beauty which comes from the harmonious order of its parts, and which a pure intelligence can grasp.